Welcome back to our biomass class, where we're delving deeper into the fascinating world of conversion of biomass resources into heat and power. This video was made with the support of InnoEnergy. Remember that this biomass energy course has 9 lessons. Lesson 5 has an introduction and several videos that go deeper in some applications of biomass combustion. After studying biomass systems for heat and power generation, let's delve into mass and energy balances, particularly in energy balances and energy efficiency. Biomass includes a wide set of materials from different origins. Let's focus on lignocellulosic solid feedstocks. Combustion is a fast oxidation reaction that releases heat. Therefore, to know the heat released by combustion, let's analyze it as a chemical reaction. Let's start by studying the heat released in the combustion reaction. In the video about combustion mass balances, we have studied the reaction of biomass with excess wet air. The heat released in the combustion reaction can be evaluated using the thermodynamic concept of enthalpy. Therefore, let's start with the definition of enthalpy. Enthalpy is the system's internal energy plus the product of its pressure and volume. In a closed system at constant pressure, the heat absorbed or released equals the change in enthalpy. Why there is a change in enthalpy when biomass burns? Because a change in the enthalpy of formation of reactants and products. So, let's define the enthalpy of formation. The standard enthalpy of formation or standard heat of formation of a compound is the change of enthalpy from the formation of 1 mole of the compound from its constituent elements, with all substances in their standard state. These values are tabulated for most pure substances. The heat of reaction is the heat released in a chemical reaction where reactants and products are at their standard state. It is the difference between the standard enthalpy of formation of products and reactants. For decombustion of carbon to produce carbon dioxide, the heat of reaction is the same that the enthalpy of formation. For biomass, this is more complex, with more reactants and products. Here, the enthalpy of formation of each component is multiplied by the number of moles. We sum the enthalpy of formation of products and the enthalpy of formation of reactants. For combustion, this difference is negative. Accordingly, with thermodynamic principles, these is called an exothermic reaction. The chemical composition of biomass is very complex. Therefore, knowing the standard enthalpy of formation is almost impossible. For this reason, we will use the lower heating value as reference, which can be determined experimentally in a pump calorimeter. The lower heating value is the standard reaction enthalpy per kilo of fuel when the final state of water is vapor. Adiabatic combustion. We say that a combustion reaction is adiabatic when there is not heat exchange with the surrounding. If there is not work released to the environment and the pressure is constant, the enthalpy of final products is equal to the enthalpy of reactants. For making the enthalpy balance, we need to know the enthalpy for fuel, air, and flue gas. The enthalpy of a given compound is its standard enthalpy of formation plus the internal energy difference between its temperature T and 298.15 Kelvin, where Cp is the specific heat at constant pressure, expressed in kilojoules per mole. For an adiabatic combustion, where the enthalpy of reactants is equal to the enthalpy of products, we have this equation. Rearranging the equation by combining the standard heat of formation of products and reactants, we can evaluate the enthalpy of products and the adiabatic temperature of combustion, or T2. Because for biomass we don't want to use the standard enthalpy of reaction but the heating value, we can use the specific heat in kilojoules per kilo and the mass fraction of each component instead of the molar fraction. Additionally, we can avoid the integration of the specific heat by using the mean specific heat between the reference temperature and the product's temperature. With this approximation, it is easy to calculate T2, the adiabatic combustion temperature. It is the maximum temperature that combustion products will reach because there is not heat released to the environment. In this expression, the sensible heat of products is equal to the lower heating value plus the sensible heat of reactants. In summary, combustion produces flue gas and ash at high temperature. T2 in the equation. Heat is provided by the fuel lower heating value plus the sensible heat of biomass and the sensible heat of air. However, this is not the scenario in a biomass combustion plant. In a combustion equipment, like a stove or a boiler, we want to produce heat. For this reason, the combustion must be a non-adiabatic one. Non-adiabatic combustion. In a non-adiabatic combustion, some heat is taken. In that case, the enthalpy of products will be below the enthalpy of reactants. If no work is produced, the difference between the inlet and the outlet enthalpy is the useful heat. Therefore, the useful heat per kilo of fuel is the lower heating value of the biomass fuel, plus the sensible heat of the air used in the combustion, plus the sensible heat of the fuel, minus the sensible heat of the combustion products at the outlet temperature. We can multiply this equation by the fuel flow rate to calculate the thermal power produced. Energy efficiency. The thermal efficiency is the ratio between the useful heat and the product of the fuel lower heating value multiplied by the fuel mass flow rate. The efficiency is 1 or 100% when all the energy contained in the biomass is converted into useful heat. However, this never happens. Let's analyze on what the energy efficiency depends on. The analysis of the energy balance reflects that the maximum energy is obtained when both reactants and products are at the standard temperature, because the definition of lower heating value. However, reactants can be at higher temperature. In that way, the useful heat increases when the air of combustion is hot. This is the reason why big combustion plants have an air preheater, where air is heated by the hot flue gas. On the other hand, the useful heat decreases with the outlet temperature of products. For biomass, the flue gas and ash. Finally, there can be some losses in the oven walls. Wrapping up. The combustion of biomass produces heat. The heat released by a kilo of biomass depends on its heating value. Because this heating value is a reference at standard conditions, we need to do an energy balance taking into account the inlet temperature of reactants and the outlet temperature of products. This is done using the material's flow rates and their specific heat. The energy balance reveals that the useful heat and the efficiency decrease with the outlet temperature of ash and flue gas, and that both increase with the inlet temperature of the combustion air. They also decrease with the thermal losses in the boiler walls. With all these data, we can calculate the thermal energy efficiency of a biomass boiler.